Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, Basics, Sign of Trigonometric Functions, Concept number 14, Quadrant 3, and Trigonometric Functions. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2. If I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose by ordering the complete cram session. You have lots of peers, classmates, friends, and colleagues who are taking Algebra 2 as well and who could really benefit from this cram session. So be sure to spread the word and tell them to inbox me at memedicine@gmail.com so that they too can order the complete cram session. You'll be glad you told them because they'll make great study buddies. And last but not least, the concept of cramming often has a negative connotation. But what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive. We're not hurrying here, we're cramming. There's a difference. Hurrying is basically taking tons and tons of unorganized information and jamming it into your mental, spiritual DNA over very tiny amounts of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way in what seems to have been an instant. So let's delve into the concept of Quadrant 3 and the trigonometric function. Quadrant 3 and trigonometric signs. Express the trigonometric functions of an angle theta in quadrant 3 as a function of its reference angle theta sub ref, short for reference angle. Definitely press pause and I'll give you a moment to think. And if you don't even know what's going on, just relax. We're going to go through it in a second, okay? Well, not exactly a second. It's an expression, you know what I'm saying? All right, so hopefully by now you were able to press pause and come up with a solution expressing the trigonometric functions. And when I say trigonometric functions, I really mean the three basic trig functions and their cofunctions, such as sine of theta and cosecant theta, the cosine of theta and secant theta, and the derived quotient trigonometric function, the tangent of theta, and its cofunction, the cotangent of theta, okay? So I mean all the basic trig functions, excluding the inverse trig functions, which actually yield an angle value as opposed to a numerical value, okay? All right, so let's tackle this issue. The signs of trigonometric values depend on the x and y coordinate of the x and y coordinate of the terminal side where the reference angle is found. So basically, which quadrant does the terminal side of the angle land in, okay? And if you're still not clear on what I'm talking about, that's okay. Everything is going to be fully expressed in an organized way. But before expressing the trigonometric functions in quadrant 3, we first need to understand the concept of standard position. And standard position occurs in quadrant 1. Doing this will simplify finding all the trigonometric values. And an angle in standard position in quadrant 1 has approximately 6 key features. The first feature is that its vertex is located at the origin, whose xy coordinate points are 0, 0, okay? So here goes our angle theta. And the initial side ray, as slightly indicated here, is located on the positive x-axis. The terminal side ray, which we're going to call R for short, terminates in quadrant 1. So it grows in the positive counterclockwise direction, making this a positive angle. And notice that this angle is also acute, meaning that it falls between the quadrantal angles 0 degrees and 90 degrees. Quadrantal angles are angles whose terminal side rays terminate on the x-axis, such as 0 degrees, or the y-axis, such as 90 degrees. You could say these are also quadrantal angles: 180 degrees, 270 degrees, 360 degrees, or if you travel in the negative clockwise direction, you'll have negative 90 degrees, negative 180 degrees, and negative 270 degrees, or negative 360 degrees, etc. You can go on and on and on, okay? But we're not going to go that deep. It's not that deep today. All right, so we're going to do a little bit of magic. We're going to turn our terminal side ray into a segment by hypothetically, or like do this in your imagination. I know you guys have great imagination, so just play along and imagine with me. Let's say we decide to cut this array off right here at this point, P short for point, and our point has the coordinates x and y. K corresponding to its x coordinate on the x-axis and its y coordinate on the y-axis, okay? Alrighty then. So we can say for our purposes that this newly formed segment travels in the horizontal direction on the x-axis to the extent of x, its x coordinate, and it rises to the level of y, its y coordinate, okay? And looky, what do we have here? After resolving our newly formed line segment into its x and y coordinate, we have an imagined right triangle. So let's just indicate that. Okay, great. And yeah, basically this structure here is what we base all our trigonometric functions in Algebra 2 on, at least when we're dealing with triangles in Cartesian coordinate planes, that is an x, y set of axes, okay? And notice that x, or the x coordinate of our segment, or what we have now as a hypotenuse, can be positive or negative. Positive in the instances where x is located in quadrant 1 and quadrant 4, but negative in the instances where x is located on the negative aspect on the x-axis in quadrants 2 and 3. For our purposes, it's going to be negative because we're dealing with quadrant 3, okay? But we're not there just yet. We could say the same for the y-coordinate, okay? So the y-coordinate is going to be positive wherever the y-axis is positive, and that occurs in quadrants 1 and quadrants 2, but negative wherever the y-axis is negative, and that occurs in quadrants 3 and 4, okay? And again, for our purposes, the y-coordinate is going to be negative because in quadrant 3, we're dealing with the negative y-axis, but we'll get to that in just a moment. Now for our hypotenuse, the cool thing is that it can never be negative because it's the measurement of a segment length, which is really a play on the distance formula that says x minus x squared plus y minus y squared. Then you take the square root of that, and that's going to give you the distance measurement, okay? And the reason why this is a play on the distance formula is because one set of points is 0, 0. Well, we don't need to say x minus 0 squared plus y minus 0 squared. That's kind of redundant. So you can just, it's implied that it's 0. That's why it's cool that for standard position, the vertex is located at 0, 0, because it makes this portion convenient, okay? All right, so squaring each coordinate takes care of any negatives. Then, unsquaring and adding the sum. Unsquaring basically undoes the squaring, but okay, whenever you see a squaring and then the taking of the square root, that's just to basically get rid of any negative signs, okay? So this will always be a positive measurement as opposed to these being coordinate locations on our Cartesian coordinate plane. All right. But again, we're not interested in quadrant 1, but we will say this, that the reference angle for an angle in standard position in quadrant 1 is just that angle itself. So 𝜃𝑟𝑒𝑓, or theta serves as its own theta reference or reference angle. That means all reference angles are basically acute angles whose initial side rate began on the positive x-axis, okay? That's like the basic definition of a reference angle. And reference angles are important because when you do inverse trig calculations in your calculator, they're actually calculating values for reference angles. You're going to have to determine whether you need to manipulate the value of the reference angle by adding or subtracting 180 degrees, 360 degrees, and so forth, okay? But I'll show you what I'm talking about in just a sec. And what you add or subtract from a reference angle depends on what quadrant you're in. So there's like different variations of reference angle values or theta values depending on which quadrant you're in, okay? All right, but we're basically interested in quadrant 3. So for any obtuse angle in quadrant 3, because all angles drawn in quadrant 3 have to be obtuse, like the thetas, not their reference angle, okay? We're going to basically say that the reference angle is the positive acute angle made with the x-axis. Positive because the angle is being formed in the clockwise direction, okay? And so the formula for finding the value of the reference angle is going to be our obtuse angle theta minus 180 degrees, the initiating quadrantal angle of quadrant 3, or you could even use the terminating angle of quadrant 3, which is 270 degrees. You could say that 𝜃𝑟𝑒𝑓 is equivalent to 270 degrees minus this obtuse angle theta, but I won't confuse you. We'll just stick to 180. Or let's say you know the reference angle in quadrant 3 and you're interested in finding out the corresponding obtuse theta value. You could say that theta, okay, is equivalent to the reference angle plus the initial quadrantal angle of quadrant 3, which is 180 degrees, okay? All right, and see here that all we did basically was do a horizontal, no, actually this is a vertical flip. Vertical flips are done about the x-axis and horizontal flips are done about the y-axis. I know it's kind of zigzag, the reasoning, but just trust me on this. Okay, I think I said this crisscross in previous sessions. So vertical flips, it's not a big deal, but you know, just so you can know the correct jargon or terms, vertical flips are done about the x-axis and horizontal flips are done over across the y-axis. So basically, well, where did I even get that vertical flippy stuff from anyway? I don't know, my brain just kind of goes all over the place. All right, so see here that we have our hypotenuse, okay, or segment length. We have the x-coordinate, which in our situation is going to be negative because it's located on the negative x-axis. And we also have our y-coordinate after we resolved our segment length, okay? And it's basically going to be negative as well because it's within the realm of the negative y-axis. So let me just go ahead and indicate a negative. So this is going to be a negative x and a negative y, okay? So now for the moment of truth, we're going to basically express all the trigonometric functions of our angle theta in terms of its reference angle, which is this bad boy right here, the positive acute angle made with the x-axis. All right. Okay. I promise you, as I promised like a gazillion times, that I'm going to get a better writing system. You know, my funds are a little janky right now. Actually, I did that. But better writing with no lag time coming soon. All right. So basically, for triangular formations found in quadrant 3, only the tangent of that specific angle theta. Right here I have theta x, but I really meant to say theta. So what I really mean is theta. Only the tangent of theta is positive, and you'll see why in a brief moment. Okay, so the sine of theta in terms of the reference angle is going to be the negative sine of 𝜃𝑟𝑒𝑓, primarily due to the fact that the y-coordinate here is negative as opposed to positive when found in standard position. So that basically equals negative y over the segment length or the hypotenuse. And remember that our r is always positive. And the cofunction cosecant of theta, we're not gonna express it in terms of 𝜃𝑟𝑒𝑓 here. For the cosecant of thetas in quadrant 3, okay, this is strictly for quadrant 3, are just going to be the reciprocal of the sine of 𝜃𝑟𝑒𝑓. So we could say the cosecant of theta in quadrant 3 is equal to the negative cosecant of 𝜃𝑟𝑒𝑓, but we're not going to write negative cosecant 𝜃𝑟𝑒𝑓 because I just don't feel like it. And that's going to be equivalent to the segment length or hypotenuse divided by our negative y-coordinate, okay? And we get the negative from the fact that we're now in the realm of the negative y-axis as opposed to the positive y-axis when we first started off with the core concept of standard position, okay? Second, we have that our cosine of theta, this obtuse theta, of course, which lands in quadrant 3, is equal to, yes, you guessed it, the negative cosine of the reference angle. The negative coming from the fact that the cosine of any angle theta is going to be the adjacent side, which corresponds to a negative x coordinate, divided by the hypotenuse, or in this case, our segment length, okay? And we have that the secant of this particular theta is going to be equal to the negative secant of theta reference, or basically just the reciprocal of the negative cosine of theta reference, which is going to be r, or the hypotenuse, divided by the adjacent side, which here corresponds to a negative x coordinate, okay? So you can kind of see the way cofunctions work. They're just basically reciprocals of the original trigonometric function. And last but not least, we said that only the tangent of theta is positive. Well, the tangent of theta is obviously equivalent to the side opposite the angle divided by the side adjacent to the angle. So the tangent of theta is basically equal to the tangent of 𝜃𝑟𝑒𝑓, all positive, as if we were here in quadrant 1. But the reasons for positivity, if that's even the correct way to express this, is because both the x-coordinates and y-coordinates are negative. So the opposite side corresponds to a negative y-coordinate, and the adjacent side corresponds to a negative x-coordinate. And thus, for the cotangent, we just take the reciprocal of the tangent of 𝜃𝑟𝑒𝑓. And so we have that the cotangent of theta equals a negative x, or the adjacent side, divided by negative y, or the opposite side, which again corresponds to a negative y coordinate. Okay? I think that's pretty much it. And as you can see, intellectual comprehension of this material was not difficult at all. And after the short amount of time it takes you to complete the entire cram session, you'll definitely be prepared to answer a battery of questions about Algebra 2. Okay? So inbox me at memedicine@gmail.com to order this complete Cram session. Good luck.